Okay, good morning. Let's get started. I hope you all enjoyed the bowling yesterday night. I did, although I was not very competitive. I think we start with a couple of announcements as far as I heard.
Yeah, I'm gonna here. Okay, should I just start? Well, I have at least just one announcement, is that on the website program, so the link's up there, you just go to the Harvard-Heidelberg Star Formation 2017 website, go to the schedule, click on the schedule, and then at the very end, we're putting up all of the documents that you've been working on in the unconference sessions. Glue is already up there, the simulation spreadsheet from 2 days ago, crowdsourced list of feedback numbers. I think we were going to put a Thor document up there. So that's item number one. Please post all of the wonderful, brilliant things you've been working on in the unconference sessions. Email us, and then we'll put it up there. And then there's also a list of restaurants for lunch today. So lunch is not going to be at FOHO today. You're on your own, so form your groups and head out. There's a list of restaurants on the schedule, and they're all about 5 minutes walk or so.
There's the photo at the beginning of the coffee break, and we'll put up the unconference sign-up thing during the coffee.
Okay, did everyone hear that? Okay, so there will be a photo after the coffee break. At the beginning, we're going to go on the steps here, right? So we're going to take the photo here. And the unconference things will be up during the coffee break. Okay.
And we will have sunshine for the photo, contrast to yesterday. So we now have a number of research talks, and we start with Blakeslee, and she will talk about from clouds to cores, and then there's a long title following.
Okay, so I'm going to be talking about the initial conditions of star formation. And I want to first start with the reminder that what we mean by initial conditions isn't so straightforward, right? Because the initial conditions are actually also related to the final conditions, right? Because ultimately, there we go, this one works better. If we think about the life cycle of gas in a galaxy, we're transitioning from this warm ionized medium to a warm and cold neutral medium, which then forms molecules, which then becomes gravitationally unstable to form stars. But then, of course, as we heard a lot yesterday, stars then have feedback onto the interstellar medium. And so this is really not such a straightforward problem to even talk about initial conditions. But the main ingredients for initial conditions of star formation that we can think about, the most basic ones would be the fact that we know the ISM is turbulent. And of course, this can be a consequence of the feedback itself. There's magnetic fields. The medium's magnetized. You can't separate that from the turbulence, as we also discussed in our unconference yesterday. The magnetic fields are tied to the dynamics of the gas. And then, of course, to form a star, one has to somehow get gravity to start working, and that can be both gravity of the galactic disk, so the galactic potential, as well as the self-gravity of the cloud. So even to talk about initial conditions is somewhat complicated. Now I'll show it as my summary of the talk. This is also my conclusions of the talk. So you'll see this slide again. In my short amount of time, I want to address initial conditions that we can observe, so the initial conditions of the gas density, and that's very nicely traced by the probability distribution functions that we've heard a lot about. Essentially, how can we understand how we transition from this log normal form of the PDF, which is given by a turbulent density field, to a density field that shows signatures of collapse, which is given in this power law form. And then also we have other indicators that we're transitioning from the initial turbulent conditions of the interstellar medium to a more gravitationally collapsing molecular medium. So that can be seen in this sort of magnetic field change. This is column density magnetic field. You go from regions which are subcritical to this rising behavior in the magnetic field with column density, which are all below this line as supercritical. And then the sort of take-home point here is that both of these two different, completely different observational signatures are actually due to the so-called post-shock density. And then finally, I'll show a new way of calculating the star formation rate based on these initial conditions, which is taking integrals of a power law PDF rather than a log normal PDF. So some basic parameters to keep in mind. We've heard a lot of these before, but just to remind you, since it's the morning and I'm going to be showing you some equations, so wake up. Sonic Mach number, right? So this is the ratio of the velocity, turbulent velocity to the sound speed. You could also think of this as a ratio of the turbulent kinetic energy to the thermal energy. The Alphen Mach number, the ratio of the turbulent velocity to the Alfvén speed. You can also think of this as a ratio of turbulent to magnetic energy. And just to remind you, for the plasma fans out there, the plasma beta is actually the ratio of those two Mach numbers, the Alphen Mach number to the sonic Mach number squared. There's also an interesting way of thinking about the so-called post-shock density, which is going to be an important parameter in this talk. The post-shock density you can also derive from the jump conditions. It's related to the sonic Mach number, and you can equate the thermal pressure to the ambient turbulent pressure to derive the post-shock density. Okay, so initial conditions, we have to talk about density, right? Because ultimately that's interesting. This is a nice movie from Daniel Price and Christoph Federath. This is a turbulent box simulation, supersonic, so you see the formation of shocks and high density features, and the corresponding PDF forms here. It's log normal. This has been observed in basically all different types of turbulent box simulations, as well as in the interstellar medium, in particular in the diffuse interstellar medium. So this is an example of neutral hydrogen in and around Perseus taken with the GALPHA survey. You see this nice log normal PDF here. This has also been seen in H-alpha, as well as other diffuse tracers. And this is an example of other turbulent box simulations with different initial conditions, different sonic Mach numbers here. And you see all of them show this nice log normal PDF, where the width of the PDF, the width of the log normal, scales with the sonic Mach number. Now, of course, when we talk about star formation, we can't ignore gravity, and gravity can change this picture. This is showing ENSO simulations run by David Collins, and this is showing the density of a supersonic simulation here. So you can see at time of 0, you just have the initial turbulent seeds for the density field. And on the right, you're showing the same rendering, but just showing the adaptive mesh refinement. So showing where the refinement is working on the very densest material. And so you can see, if you watch this movie enough times as I have, you see initially at that first time step, you already have filaments. You already have these seeds for the collapsing regions. And once gravity is turned on, it just simply pulls in the very densest filamentary regions. And these filaments are actually, long-lived. I mean, this is at least a structure that's existing on a free fall time of the simulation. And then you see, of course, the formation of these denser structures as the simulation persists. So if we put this picture together of the probability distribution function of the initial density and the turbulent density, we actually get a picture, both in observations and simulations, that looks a bit like this. This is the H1 PDF in and around Perseus, taken with the GALPHA survey, shown in red. So you see this nice log normal PDF. And this log normal is pretty much a stable shape, regardless of if you change the cloud boundaries, etc. There are some complications with making an H1 PDF, and I'll mention that in just a second. But anyway, you see this nice log normal form, which is what you expect from supersonic turbulence. And if you look at the total gas and dust, this is the black line here. This is, again, in and around the Perseus molecular cloud. You see this nice log normal shape, and then a transition at some point to a power law tail. And again, this is what we see in the simulations that have turbulence plus gravity. Now, the interesting thing is we also see there's a transition point, right? At some column density, and this is in units of AV, at some AV you have a transition from a log normal to a power law tail. And you see that both in the total gas and dust traced with the black line and in this red line here, the H1 PDF starts to rapidly fall off past that transition point. So this makes sense, right? You're going from a H1 dominated medium and at some point transitioning to a molecular dominated medium. And it seems that the molecular dominated medium is mostly what we see building up this power law tail. It's not so much the H1, right? The H1 drops off very rapidly. This example is for Perseus. Now I can also show you the example for other molecular clouds. This was a work led by Nia Imara. She studied the H1 and dust PDFs in and around a number of different clouds. And as I said, the H1 PDFs can be complicated, and that's shown in these pink lines here. This is all the H1 along the line of sight. So you're right, you somehow have to associate the H1 with the molecular cloud, and so we do that with a velocity selection. So that's the red line here. This is the H1 we think is associated with the GMCs. And it shows a nice log normal form, and then at some point a transition in the dust to a power law. So this is something that we see in a number of different nearby clouds. Now recently we wanted to understand a bit more about this transition point between the log normal and the power law tail, how these initial conditions translate into this collapsing part of the density PDF. And so for this, one can imagine that the PDF is a piecewise PDF, right? You have a log normal portion, and then at some transition point you have a power law portion. And so you can solve analytically this an expression for the transition point, which depends on the slope, the mean density, and the width of the PDF, the width of the log normal. And then from there, you can relate that back to the physics that we've learned from simulations, like the width of the PDF is related to the sonic Mach number and the driving. And then, of course, the sonic Mach number one can write down in terms of this post-shock density. And then one can relate the transition point, now in terms of column density here, to the post-shock density through this sort of scaling. It depends on the slope of the power law and the width of the log normal portion. So does this analytic sort of expression work? Well, we can actually test that with simulations. And here I'm showing you a number of simulations that was led by Philip Motz. I showed some of these in the unconference the other day. These are MHD simulations that include gravity and magnetic fields. All these different simulations, I'm showing you 4 of them here. So they go down from the largest scales to the smallest scales. This is about the 5 parsec scales, the cloud scales, all the way down to 1,000 AU at the protostellar scales. All these simulations are identical in all their setup parameters except for the magnetic field strength. So this is the weak magnetic field run, 1.2 microgauss, 12 microgauss, 36 microgauss, 120 microgauss. So this is a very superalphinic, very weak magnetic field all the way to a subalphinic, very strong magnetic field. So we can study how the collapse proceeds in these simulations, if the collapse has anything to do with the physics, like the post-shock density or the sonic scale. And we have indeed seen that collapse in these simulations happens roughly at the post-shock density, at least in the trans and subalphinic runs, or sorry, trans and superalphinic runs. So here I'm showing you the plot of magnetic field in these simulations and density. And these are very similar to the very famous plots by Dick Crutcher, but this is in one of our simulations. The yellow line here represents the mean field for each density bin. And you can see roughly around the post-shock density, you get this upturn. You get this change in the behavior of the magnetic field. So this, I think, is an indicator that you're going from a diffuse ISM. This would be traced by a tracer like H1, all the way now to more dense molecular tracers, which gravity is starting to take over the dynamics. Similarly, in this inset here, this is the probability distribution function. So you have this nice log normal form, and then at some point, and this line here indicates the post-shock density, you get a transition to a power law tail. So this post-shock density, at least in our simulations, does seem to indicate the onset of gravitational collapse. Now, there's also the issue of the power law tail slope. So here I'm showing you in the INZO simulations the power law tail slope here, and then units of time here and units of the free fall time. And the different points here are the different values from the MHD simulations. So you can see this nice result that's been known both in simulations and observations, that as the power law tail becomes more shallow, the cloud becomes more evolved gravitationally. And I've overplotted some known values of molecular clouds from Herschel observations, and then their corresponding YSO counts. So there does seem to be an evolutionary correlation between how shallow the power law slope is and how evolved the cloud is. And Charlie also mentioned that yesterday. So this is interesting, right? Because if the clouds that are collapsing, that are self-gravitating, have power law PDFs, then that means the star formation rate should not be taken from a log normal, but rather it should be taken from the power law form. The log normal portion basically is set by the diffuse H1, which is most likely not self-gravitating. And all of our kind of analytic theories of star formation, and I've listed a number of references here, these are based on integrals over the turbulent density PDF, which is taken to be a log normal, right? And so here's one such example of that. Now instead, what if we take a power law PDF? Well, instead of a log normal here, we just take past some transition point, which is given by the post-shock density, we integrate over a log normal, and then we can plot the star formation rate, which is now a function of the slope of the power law PDF, which of course changes with time. And so I'll just show you that very quickly. Here is the power law slope and the star formation rate given by the analytic model here with the lines. So these three different lines are different cloud masses. This is a 10 to the 4, 10 to the 5, and 10 to the 6 cloud mass. And then I've overplotted here different molecular clouds. Both of these different compilations are from papers by Charlie, and Charlie and collaborators. So the alpha parameter, so the PDF power law slope for these different clouds is measured, as well as the star formation rate measured from YSO counts. Okay, so these lines here, these lines of the analytic model are not fits. So this is just what the data gives, and these are the model values. So it seems that we have pretty good correspondence. And so I'll conclude there. Again, you saw this slide. This was the outline of the talk. So the take-home points are listed here. I think we're getting closer to really understanding the initial conditions from the diffuse warm and cold medium transitioning into the molecular self-gravitating medium. The post-shock density does seem to be an important parameter for this, and we actually have ways of measuring this observationally now. And I think this is leading us, all this knowledge, both from the observations and simulations, is leading us to have a better understanding of how we can analytically calculate the star formation rate as well as other quantities. Thank you.
So, thank you very much. We have time for a couple of questions. Phil?
Lexi, can you explain a little more what you mean by the post-shock density? How literally should that phrase be interpreted? Does it reflect the passage of one shock, many shocks? What would it look like? Is it a dense core? Is it a ridge in a filament? Can you give us some more insight?
Yeah, so it could be interpreted as the density past a shock. Now, of course, you have multiple interacting shocks. I mean, it's literally you take the thermal pressure equal to the ambient turbulent pressure. So this would be, you could also calculate this as a function of scale, and then one could also write down a sonic scale if you were to write it down in terms of a Larson kind of relation. But the way I was writing it there was comparing the turbulent support on the large scale of the cloud to the thermal support, so the sound speed. The approximation I was using was also isothermal, so that could also be another complication. But you can also think of it, if you want to think of it in a scale-dependent way, as a relation also to the sonic scale.
So would it be the density at which the thermal and non-thermal parts that align with
I think so. Yeah, I think so.
So I wonder what kind of ingredient is missing there, because there is one exception always which puzzles me. There is the musca starless filament, which has a very shallow slope, so it really has a very shallow polymer tail and no star formation at all. So this is kind of, this doesn't fit in the picture. So, but musca is so beautiful, so easy to analyze. So what's the missing ingredient that this is not explained? Because you have no star formation and but a very shallow tail. It's an exception, okay, that is true, but it's always puzzling me.
Yeah, I mean, that's interesting. So I'm not trying to claim that the only thing that can affect the power law slope is gravity. There could be other physical processes that could be at work in musca. So that would be maybe an interesting case to take a look at and compare the analytical models to. Yeah, we could see if they fit or not. And then that could maybe be telling us something interesting about the physics that's particular to that region.
I mean, another important thing is if you talk about high density, it's always density contrast. So one has to be a bit careful that there's no one number in a way. The integral you also showed.
Mm-hmm.
I think that's also important. And if you have feedback process, of course, that doesn't apply to musca. That also impacting the slope.
Right. So these
are
are
stars have formed, then.
Yeah, although I think the nice thing about writing, at least in terms of the integral over the power law portion, is that evolves as well. So the slope evolves. So at some point the slope could evolve to the point where feedback is affecting it rather than gravity. And then one needs to shut off that.
Exactly.
Right.
Yeah. Okay, so thank you again. So that leads us to feedback. Next speaker is Stefan Reisel, and he will talk about feedback process, a new tool.
Remind me, what is the pointer? So yeah, actually today I will not just talk about radiative feedback, but about dust is relevant for many astrophysical processes, for example, heating and cooling, allowing to take for the star formation to take place in the first place. It's important in astrochemistry as a catalyst for forming of molecule. It might play a role in radiative feedback, but most important or most interesting for observations is that non-spherical dust grains align with the magnetic field directions, and this leads to all kinds of polarization effects, and observing dust polarization in turn would then allow to learn something about the projected magnetic field. The way we model all these phenomena is with the Polaris code, and basic ideas to use an input model, for example, MHD simulation, perform some Monte Carlo runs, and then create synthetic observations. So the code can actually calculate radiative pressure as well as all the numerous polarization effects related to non-spherical dust grains aligned with the magnetic field direction, including all the grain alignment theories that have been proposed so far over the years. But we can also do line molecular line transfer, including Zeeman effect, which means we can also predict the line of sight magnetic field strength. And some upcoming feature is synchrotron radiation, and also the Goldreich-Kalifas effect in the near future. So coming back to radiative feedback. So in one of my latest papers, we investigated the role of dust in radiative feedback. So imagine we have a cluster within a cloud sending out some photons. The photons scatter multiple times, pushing the dust component outwards. So one way to model this problem is with the simple approach, which is basically the volumetric luminosity as well as some averaged cross-section. But for this, we need to make some assumptions, and we wanted to investigate how good these assumptions are. And this we did with some Monte Carlo processes of scattering and dust heating, and this is the approach we use. So this is basically also the averaging process for different materials, dust grain sizes, and wavelengths. And the real difference is that we do not use the volumetric luminosity, but we actually look at each position what's going on with the radiation. So this simple model might indicate we use a 1D model, but it's a 3D model where we add up all the contributions of scattering and dust re-emission. So here we have the cross-section, the cross-sections of one of our dust models over wavelengths, and here we have the PDF for absorption and the emission. So what this basically means, if you absorb a photon at about 10 Kelvin, then it most probably ends up somewhere here about 300 micron. And what this means in the beginning, here we have the SED for the input cluster. The cloud is optical depth. We have a high optical depth because we are somewhat here, but we have a continuous process of absorption and re-emission. And finally, we end up here where the cloud is optically thin and the dust and the radiation can easily escape. And here you can see the resulting SEDs for different kind of dust grain models. And with this kind of approach, we finally could quantify some of the assumptions. For example, how often does the radiation actually scatter on dust? So it's most likely not more than 2 times for different, this is true for different kind of models, and then it gets absorbed once and then ends up here somewhere in the mid-infrared. And here you can see in this band, this is the radiative force on an average size dust grain without the thermal redistribution of dust. And if we consider the thermal redistribution, then the radiative force goes down by about 2 orders of magnitude, and as a side effect, it doesn't follow anymore a strictly 1 over r squared law. However, the main focus of my research is not radiative feedback, it's dust polarization. So here we have a simulation of an outflow. Here you can see that in the center we have a disk, and the outflows in the surrounding medium. This panel shows density, and this one shows the corresponding dust temperature. And here you have a 3D presentation of the emerging magnetic field morphology. So we have a toroidal component in the center and an hourglass-shaped component on the outside. And the question we wanted to answer here, is it actually possible to observe the toroidal component with dust polarization? Because the toroidal component is embedded in the outflow and surrounded by a large-scale magnetic field. So we had to deal with all kinds of effects related to dust observations. One of this is the projection effect, so as this sketch shows. If you have the magnetic fields all parallel along the line of sight, you have a polarization signal, and since all the dust grains emit perpendicular to it. But if you have crossing field lines, then different contributions can cancel each other out, and you have no polarization signal at all. So here it is blue star-like pattern is an analytical representation of an hourglass field looking along the symmetry axis of my 2014 paper. And if you get some inclination, and then you get this complicated pattern of crossing field lines. And it's the same for our MHD simulation. Looking along the outflow lobe, you see that you can see here this star-like pattern in emission, but going to different inclinations, here some additional lobes in the as a minimum in linear polarization. 3 minutes, okay. In linear polarization, which means here you cannot learn anything about magnetic field morphology because you don't have a polarization signal on the other head side, as I could have shown on the, in the 2014 paper, these two outflow lobes are characteristic for hourglass-shaped magnetic fields. So in the end, it actually can tell you something about the overall magnetic field. On the outside, so here you have a sketch of the magnetic field in the dust grain alignment. Here in the outside, we have the hourglass field. Here we have the toroidal component. And you have polarization because of extinction in the UV and the optical, and because, this is a polarization mechanism parallel to the magnetic field. And in thermal remission, you have polarization perpendicular to the magnetic field in the infrared at sub-millimeter, but there should be an intermediate region with, where you have both effects, and this is what we intended to model here. Here at 46 micron, you have the thermal emission in the outside, while the interior is still in dichroic extinction at 93 micron. You have dichroic extinction along the outflow lobes. And here at 1.3 millimeter, you can be sure that everything is due to thermal emission. And we analyze the lines of sight, and we can be sure that what we see here is actually the interior of the outflow lobe, while here this is a kind of dangerous image because this is not what you expect from comparing it to the sketch. This is the outside hourglass field, but in two different polarization mechanisms. This is especially relevant when this is close to the band E of the Hawk plus Sophia instrument, and this is for ALMA. So with Hawk plus you cannot observe it, with ALMA you can. So maybe 1 more minute. So you can see different orientation between magnetic fields and in filaments, as a parallel, as a perpendicular to the magnetic field strength. And this is also something what we intend to model with a simple cylindrical model, and assuming different magnetic field morphologies. And with radiative transfer, what we can do is actually predict what these different magnetic field morphologies would look like in orientation as well as magnitude of linear polarization. But however, we have still some ambiguities here. So another way we can tackle this problem is with performing additional simulations of Zeeman profiles, observing the V and I component of this Zeeman effect allows you to get the line of sight magnetic field strength. And the interesting thing here is that you get actually a sign. So you can say if it's parallel to the line of sight or anti-parallel to the line of sight, which makes it also interesting to inferring the underlying magnetic field morphology in filaments. And here is one result in OH, but we also considered different traces, and you can see that actually you can distinguish different kind of magnetic field morphologies also from radial Zeeman profiles. So the point of this project is not it's one where it is a helical field or it is a other kind of field. What we want to do here is to provide some catalog for observers to say if it is a helical field, this is what it would look like. And with that, thank you very much for your attention.
Thank you. Questions?
Just a comment on the tracing magnetic field along outflows, maybe using the line polarization to collapse this chloride collapse. Another useful way of tracing.
Yeah, but this is ongoing work. We are currently implementing it in the Polaris code. This was a tool that was not available in the results I showed you.
Yeah. And in fact, there's a paper by Taozong Jing and Xuping Lai and myself reporting this exact CO polarization in NGC 1333 IS4A. That looks like they're helical magnetic fields.
Yeah, this is what people claim by observation and theory, but we wanted to show what are the conditions where we can actually see it. Yeah.
just would like to attract your attention that in the gold effect, I claim exists only for really symmetric grains. As soon as you introduce asymmetries, grains get helicities, and in the flow they behave differently, and the alignment is different. So this is first thing. Another thing is, for classical grains, larger than 10 to the minus 5 centimeters, it's really very difficult to have pure David Green-style alignment. Really different. Even if you have superferromagnetic conclusions, in this case, nevertheless, it is magnetic ride.
Yeah,
moving into your talk.
I totally agree. I just mentioned the effects because we have implemented in the code, but all the polarization maps I showed you here is calculated just with threads.
So the observers, Mark and I,
Yeah.
have seen that what matters. I mean, this is wonderful. If you can really do this, this is wonderful. Let me say that. But the thing that matters the most is the variation in conditions along the line of sight in terms of density and dust grain properties and radiation field and all of that. And so, do you know that also in this model, or do you, when you say you model all these processes, how do you decide how efficient any one process is under the conditions that exist along the line of sight you're observing to make the synthetic polarization?
I mean, the rough approach is that we just put as much physics in it as possible, and then the efficiencies emerge on their own.
Right,
so
so
we
what I'm
don't
asking
need
is, can you tell what those are? Have you looked at that?
Yeah, in looking into the 2017 B paper, AA paper, for this we actually analyzed the line of sights and to see where the polarization comes from, so that we can be sure this is actually the interior of the outer globe and not something else. So we performed the analysis along the line of sight, considering all the conditions, density, temperature, alignment, efficiency, to be sure that this is actually the interior of the outer globe. So yeah, we analyzed this in detail, if this is your question.
I'm afraid that we have to stop here, so thank you again. It's always nice to have guests meetings. Thanks, Rosalind from Madison, talking about magnetic fields.
Okay, people can call me traitor because I was working so long and so intensively on polarization, grain alignment, and now I'm suggesting something which can be a strong competitor to the traditional ways of studying magnetic fields. I'm going to talk about gradients of velocity as a new way of tracing magnetic fields. And actually I came to this idea listening a talk of Edith Folgeron, with whom I usually disagree. She was talking about these vortices, and I said, oh, well, vortices can be, but these vortices should be aligned with magnetic fields, because magnetic fields are important. And these are my collaborators who did a lot of research with me on this topic. So, these are the works that we've done, and you see everything is very recent. And there are also some papers which we researched during the summer. And this is a disaster, because I had this bunch of young students who never wrote anything, and I gave them projects. I told them this is a gold mine. It's easy to obtain results. They obtained the results. They wrote something impossible to read. It's partially done, and it slowed me very much eventually. But I hope I will manage with that. So, this meeting about star formation, but star formation is an important corner in this diagram, but it's not all. There are many other things where magnetic fields are very important, and we would like to have the whole ecosystem of magnetic field. Well, Blakesley already told you that we live in a turbulent world, and we should take into account this. And this turbulence is happening because we have large Reynolds number, and it's really, really large. So we should take into account properties of turbulence and see what it can tell us. These are simulations which visualize the velocities. These are either contours of velocity in MHD simulations. What you see, this is magnetic field and velocity gradients, if you calculate gradients, are perpendicular to magnetic fields. And this follows also from Goldberg-Seidha model. Interestingly enough, Goldberg-Seidha model in its original configuration deals with a mean field. But later we found that it should be alignment of all these structures in terms of the local magnetic field. And this is big, because we can, with this technique, understand details of the magnetic fields, follow the detailed structure of magnetic field. By the way, this local effect were confirmed later in the numerical simulations.
Alex, in this picture, you see the velocity gradient is this way, and those are velocity contours? But
These are velocity, either contours of...
which way is the stuff actually going?
This is, it's not going anywhere. It's, you drive really violently the things, but what magnetic fields are doing, magnetic fields are mixing. Magnetic fields, the easiest way for magnetic fields to behave in response to this random driving is to do this. What people were not understanding and why they were not considering all this, they were considering if you mix them, what will happen? You will create knots. What we found that turbulent connection removes this knot, and therefore you can easily mix up magnetic field lines perpendicular to their local direction.
Of the field.
Yeah, and therefore gradients trace local direction of magnetic field. Okay, so this is a prediction of the Goldberg-Seidha Kolmogorov actually motions perpendicular to magnetic field lines. Take the gradient of this, it gives you negative power, minus 2/3 of the perpendicular direction. It means the smaller the gradient we are measuring, on the smaller scale we're measuring the gradient, the larger the gradient. Therefore, the gradients at the resolution scale are dominating, and we are following magnetic fields at the resolution scale. We surely cannot measure three-dimensional gradients, but we can measure two-dimensional gradients using, for example, centroids, a traditional way of measuring velocity in projection. This is gradients of centroids. Or we can take velocity slices, velocity channel maps. And in our work with Dmitry Pogossian, we proved that thin velocity channel maps are dominated by velocities. Okay, so what is happening? This is our numerical simulation, which shows that in diffuse region, when we have Goldberg-Seidha processes, the whole Goldberg-Seidha turbulence, we have gradients that are shown here, they're turned 90 degrees. Just to have a good comparison. They follow magnetic field, these turned gradients. But in the gravitating regions, everything is changing, and this is understandable. You have acceleration either along magnetic field lines, or if magnetic field is strong, or everything is collapsing, you have acceleration of everything. And in this case, gradients are parallel to magnetic field, and therefore you see them perpendicular to the magnetic streamlines, which are shown by textures here. To characterize this quantitatively, we introduce a measure which we called alignment measure, where we have magnetic fields, and this is a direction between the velocity gradients, again turned 90 degrees. And if we have perfect alignment, we have alignment measure 1. No alignment, we have 0. So this is how it works. This is gradients. This is polarization textures. And this is another technique which was suggested by Susan Clark and collaborators, based on filaments. What we see here, there is a good correspondence. Alignment measure that we get in H1 was 0.76, for filaments 0.47. So gradients trace much better magnetic fields than filaments. If we go to, let's say, VLSC, we get gradients 0.9, very good alignment, and alignment measure of filaments minus 0.07, essentially 0. So there is no alignment of filaments and magnetic fields, but there is a very good alignment for gradients. This is torus. Also, well, we don't have really nice maps of polarization. This is starlight polarization, but we see filaments fail completely. But we can see that gradients are consistent with this starlight. These are the intensity, density colors. This is a usual way of presenting.
What else? I'm really trying to understand. What else are we supposed to see in the plots?
This is polarization textures. Planck made them very popular. I don't really like them, but people are using them, and why not? Okay, I follow the bandwagon. But these are our gradient, this is polarization, and these are filaments. These are the same approaches. But by the way, our technique is very different from the technique suggested by Planck collaboration and Planck's. It has its own, pluses. But for example, here we show the structures that for torus, and here it's more or less consistent with what we see, but if we apply HRO, we see various dots. Okay, so what we can see, what we can do now? We can do surveys using this. This is our initiation of a survey with a number of clouds that we initiated. What we can do also, we can use both galactic rotation curves and different species to have 3D maps of magnetic fields. Well, we can study something where we will never be able to study with, for example, aligned grays. This is Smith cloud, high velocity cloud, which is only seen in velocity space. By the way, these are also magnetic fields that we predict. And interestingly enough, we also predict that density gradients and velocity should be perpendicular, and we see this. This is, can we combine velocity and density? Yes, we can combine. And this is application where Green's density gradients, which show shocks. So what we can do, we can find the magnetic field direction and strength. We can identify shocks. We can identify self-gravitational region, and we developed a number of techniques to improve our alignment. I don't have time to discuss this table. It compares our gradient technique with the accepted ways of studying alignment. It has some advantages. Our technique has sister techniques. We use synchrotron intensity rather than polarization, and then we don't depend on the Faraday rotation. We can just get magnetic field directly, which also has advantages. We are trying now to learn machines to do this, to improve our finding magnetic fields and putting all our knowledge of turbulence there. We can find magnetic field strength using the technique, not using any polarization, just only spectroscopic information. And this is my last slide. From finding, understanding turbulent connection, we can have better understanding of turbulence. And this is one of the outshoots, is the gradient technique with many applications. This is a Smith cloud, and I put it also on my badge.
Thank you, Alex, for introducing a new technique. Questions?
Well, Alex, ultimately, the anisotropy is coming from MHD turbines, and ultimately that is because you've got waves, a spectrum of waves propagating through, right? So
I would not say these are waves because they live only one period. These are eddies. And these are eddies, as I showed. These are eddies which are mixing magnetic field lines perpendicular to their direction.
but those that decouple, I mean, the MHD turbines gets nonlinear, where you're coupling these modes, and that's what's creating the anisotropy.
In this situation, it's happening anisotropy because it's much more easy to mix up magnetic field lines rather than bend them. It's very difficult to bend very strong magnetic field, but it's easy to mix the magnetic field lines. And in my understanding, this is the reason that we have very strong anisotropy in MHD turbines.
Alex, in terms of Dick Crutcher's density, field strength versus density plot, famous plot, where on that diagram should this technique be useful and where should it be not useful?
We're exploring where it is useful. I hope it can be useful everywhere. We'll see.
But I mean, in the lowest density, in the highest density regions.
In the highest density regions, there are interesting effects. And this is, we already studied this, and it provides us with additional ways of studying magnetic field independence. Decoupling gives us additional ways of studying magnetic fields with gradients.
But you would not see the gradient effect as
But we see differences of the gradients in neutrals and ions. And this gives us a very interesting way to study magnetic fields.
Okay, if there are no other questions, thank you again. You already heard the word machine learning, and Juan is taking that up again. And that's actually a new type of talk, so combined research and training talk.
Hello, good morning. How are you guys today? So I'm going to show you a few pretty pictures, and I'm going to mention a few buzzwords, and hopefully this will work. Oh, well, where is my presentation? Okay. Yeah, so the title of this presentation is composed of 3 items. Machine vision, on which I'm not a specialist, the interstellar magnetic field, and the process of molecular cloud formation. But since this is a framing talk, I'm going to talk mostly about the work that we have already done in the interstellar magnetic field using Planck. and hopefully you'll learn something about machine vision. I probably will learn too about machine vision as I take you in this path of learning what we did with Planck. So of course this is not a work that I did by myself. So I'm indebted to the Planck collaboration. Also there's going to be some work on simulations that's led by Patrick Enevel. I'm also part of BLASTPOL. And now, hopefully by the end of this talk, I can suggest how can we use the same techniques that we use to study the magnetic field in the study of emission by neutral hydrogen. So let's begin with this picture that is pretty much the summary of my talk. This is a map of the magnetic field projected along the line of sight and integrated along the line of sight and projected on the plane of the sky as inferred from the Planck observation of polarization and 353 gigahertz. Okay, we just rotate those polarization vectors, and there's many of your favorite clouds that live in this big projection. Here is Orion, here is Taurus, here is the California, here is Perseus, here is the Orion-Eridanus bubble. So I'm going to explain you what we did with these maps, how we made sense of all of this, and how we expanded the techniques that we had to study these kind of maps. There's no way you can lay this transfer your way out of analyzing this data. So I'm going to tell you a little bit about what we did. Of course, Planck is a big collaboration of many people, and every time I give a talk about Planck for the rest of my life, I have to show this slide. So if you're not familiar with Planck, Planck is this telescope. It was launched in May of 2009 from Kourou in the French Guiana. It was in the same rocket as Herschel. And it observed during 4 years all of the sky in frequencies of radio and submillimeter from a point between the orbit of the Earth and the orbit of Mars. So this is not Planck attacking the universe with an evil beam. This is actually the beam of Planck, and it's reconstructing the emission in those frequencies over the whole sky. Okay, it did this 4 times over the whole sky, and the maps that you're going to see of polarization were made only with 8 detectors. Only 8 bolometers made the maps that I will show you at 353. So yeah, Planck has 9 frequencies that go from the radio to the submillimeter. So you know you're sensitive down here to the synchrotron and free to the CMB, and up here you're more sensitive to dust. So you can see in the cleanest patch of the sky, you can get to see the CMB, but you're dominated by the emission of the dust and the synchrotron emission from the galactic plane and all of the local structures. Out of those 9 frequencies, 7 of them were sensitive to polarization. And when you look at the sky in polarization, what you're seeing is a combination of the CMB that has its own polarization. At high frequencies, you're seeing the polarized emission by dust, and at low frequency, you're seeing the emission by synchrotron. Okay? So if you take the emission, the polarized emission at the highest frequency, you can study the emission of interstellar dust. So the observables of polarization are Q and U, the Stokes parameters that establish the linear polarization of light. So one of the observables is the amount of polarized light that you get. This is one of the observables. So this papaya diagram, remember, is the whole sky unfolded. So of course you see more polarized light, more linearly polarized light from the places in the sky where you have the most dust. So no surprise. So what you can do is just divide the amount of linearly polarized light by the intensity at the same frequency and see what is the percentage of polarization of that light. So one of the first discoveries of Planck, the most important, is that the polarization of dust in this frequency can go as high as 40%. And then there's really large patches of the sky that have very large polarization. For example, there's the Fand region where the polarization percentage is in average 15. Then you have the Northern Galactic Spur. And the reason why I mask these patches is, of course, because you have less dust here. So the map becomes noisy. So in order to present you this map and for you to really have a reliable estimation of this parameter, I had to smooth the data to 1 degree. If you want to have reliable estimations of the polarization fraction up here, you have to smooth the data to 2 degrees and up to 5 degrees to really extract the information at high galactic latitude. The other observable that we have is related to the magnetic field. So you have the amount of polarized light, but you also have the direction of polarized light. So Stefan already showed a similar diagram. If we assume that the magnetic field is aligning the dust grains, and you have a source the extinction of that source, if this is a star, and these lines are just the plane of emission of that light, the absorption is going to be parallel to the magnetic field, and the emission is going to be perpendicular to the magnetic field. So in principle, you can take that orientation of the emission of polarized light rotated by 90 degrees and make the nice maps that I've been showing you. So how does that look in the sky? It looks like this. This is a pattern that we produce with an algorithm that is called line integral convolution. Basically, we're just joining the dots of all of the possible vectors. So this is the new way that we have devised for visualizing the Planck maps, but you shouldn't do science with this, okay? This is great if you want to illustrate how the polarization looks, but the real science is done with Q and U, okay? So with that in mind, you can also do pretty pictures. So this is the picture that you guys have seen before. This is a picture of the dust column density as inferred from Planck. So darker colors indicate more dust along the line of sight. Cyan and blue indicate less dust along the line of sight. And the direction of this drapery pattern is just the direction of the magnetic field. Okay? So far, so good? Great. So we did several things, and the power of Planck in terms of a star formation, it allows us to sample fine detail of the magnetic field in molecular clouds. So just as a comparison, this was the largest map of a molecular cloud made before Planck. This was made with the Spiral instrument in the South Pole telescope at 450 microns. And this is the Pipe Nebula. This was the largest map of dust polarization of a molecular cloud that was made before Planck. Okay? This dot is the beam of Planck. So the beam of Planck is 5 arc minutes nominally, but for most of these molecular clouds, we had to smooth to 10 arc minutes. That means that we're resolving only scales of 0.4 parsecs, okay, for nearby objects. And of course, if they're further away, you're washing away most information. The whiskers here correspond to the observations of a starlight polarization, okay? So Planck is not only penetrating inside of the cloud where you don't have observations of starlight polarization simply because it's absorbed, but also we have far way more statistics than any other survey of polarization before towards a molecular cloud. So what do we do with that besides postcards? Well, we wrote a whole bunch of papers. And many of those papers are devoted to the study of the magnetic field. So some people say that the Planck papers are like the Marcel Proust novels. They have Roman numerals, they have attractive titles, and you only read them when you're desperate. But the Planck papers are more like the Harry Potter novels because they all have like common characters. And by Planck rules, all of them have to agree with each other. So when you read a Planck paper and somebody defines something, it's the same definition for all of the Planck papers. So if you can read them like a novel, they do great for these vacations. Maybe you want to consider them. And if you want to get them for free, you can go to this website, Planck and the magnetic field.info. There we put the abstracts, there we put the prettiest pictures, and you can just go over the Planck results. Of course, not all of them are relevant for the study of molecular clouds and star formation, but many of them are. But you can learn about the polarization fraction, about the polarization spectrum, about E and B modes in dust, so you can go there. And now I'm only going to talk about the Planck papers that are related to the relative orientation between the magnetic field and the column density structure in molecular clouds. Why? Because we think that may be important to learn about the role of the magnetic field in the assembly of these molecular clouds where we know star formation is happening. Okay, so when I talk about relative orientations, it's between the magnetic field and column density structures. So how do we study that? So we did a first study over the whole sky. So we selected some structures, and I'm going to tell you about how we selected those structures. And we analyzed what is the relative orientation of those structures that we selected. So you can guess, we removed the galactic plane because it's too confused. And then we removed some background. We didn't do background structure. We just checked places where we know that the polarized emission is probably larger than the emission from the background. And there we calculated this horrible thing called the Hessian matrix. So these are just double derivatives of the column density. And this is a way of evaluating stuff that is filamentary. It's just a way of evaluating filaments. So when we did that, we identified fellows like this one. This is a super long filament. This is more than 20 degrees in the sky. That is next to the Large Magellanic Cloud. And then you can see many of the effects that we see in Planck. You see the component of the galactic plane. So you see a magnetic field that is aligned with the galactic plane. Of course, we cannot see directly to the Large Magellanic Cloud because it's too far and there's too much dust between us and this object to really disentangle the magnetic field there. But there's these really long structures along which the magnetic field is also running. So you have alignment of the magnetic field and the column density. We did that over the whole sky. And we summarized that using a histogram. So this is a histogram of the angle between the main axis of those filaments and the direction of the magnetic field. And that histogram peaks around 0. So we see structures that are mostly parallel to the magnetic field. Then we invented this parameter. We just basically counted how many counts of the histogram are in the center, so parallel, and how many counts are in the sides, so perpendicular. So if this parameter is positive, you mean the structures mainly parallel to the magnetic field. And if this parameter is negative, the structure is merely perpendicular. And this is important for what comes next. I'm going to be talking about this parameter a lot. So there is this plot that is a bit complicated to understand, but don't worry, it's easy. So in this axis, you have column density. So you're going to higher and higher column density structures, and you see low values of this parameter. You see no particular relative orientation between the magnetic field and the column density structures at high column densities, using this technique of the Hessian matrix. As you go to lower column densities, so in this direction, you see that you're more aligned with the magnetic field. And that changes also with the polarization fraction. So if you go to a region that has very high polarization fraction and has very low column density, is very aligned with the magnetic field. Okay? And the same trend occurs in this direction. So maybe we can just marginalize over one axis and present this. So if you take the whole sky, the relative orientation goes between mostly parallel for the low column densities, and as you advance to higher and higher column densities, you find that there's no preferred relative orientation over the whole sky at the high column densities. And the high column densities are kind of important because these are the molecular clouds. Okay? But remember the way we have been calculating the relative orientations. This is the Hessian matrix. So this is the way we have been doing stuff. We just make a stick and calculate how the stick is oriented with respect to the magnetic field. And that's exactly what we did. So in this paper led by Doris Arsumanian, she just took her favorite filaments, because that's kind of the way we selected them, and then she checked what is the relative orientation of the magnetic field with respect to those 3 filaments that she selected. So what she found is the filaments of the highest column density. This guy, this is the Mosca region, and this is B221 in Taurus. They are perpendicular to the magnetic field. If you take another one of her favorite filaments that is at a lower column density, what she finds is that actually the magnetic field there is parallel to that filament. Okay? But this is kind of arbitrary, no? We're just decomposing something that is not obviously just a few filaments first by eye or using the Hessian matrix, and we're ignoring the whole complexity of the clouds. Actually, molecular clouds look like this. They have lots of different features which have different orientations with respect to the magnetic field. That's where machine learning entered. Well, it has nothing to do with machine learning. This is human learning up to this point. So what we did is devise a method that allows us to study the whole molecular cloud without assuming some filamentary structure, just using the information that we have from the column density map. Okay, so this method works as it goes. So if you do simulations, this is 3D. If you're an observer, you can just go to this panel. This is the projection of that. So this works both in 3D and 2D. Don't be nervous. So what is the problem that you have? You have a scalar field, the density, and then you have a vector field, the magnetic field. And you want to know the relative orientation between those two. So an easy way of doing that is calculating the gradient of your scalar field. You can add complexity to how you calculate that gradient. You can make it in a larger, smaller vicinity. You can play around with that. And then you have 2 vector fields. When you have those 2 vector fields, pixel by pixel, independent observation by independent observation, you can calculate what is the relative orientation angle between those 2 vectors. Okay? And then you can summarize that in a histogram. That is the method. It's called histogram of relative orientation. So do we really learn anything about this? This sounds really cute, but do you learn physics from this? Well, oh, this is so passe. Okay. Now, so what we did is we took 2 simulations of a portion of a molecular cloud. And what we tried to do was evaluate the relative orientation and check if the magnetization does anything to the relative orientation. So for the rest of the talk, I'm going to be presenting simulations that look a lot like observations. So if you feel nervous and then you see a spherical cloud, that means it's a simulation. Okay? So don't be confused. Just always go back to the corner. If there's a spherical cloud, it's a simulation. So what we did is in 3D, if you calculate the relative orientation between the magnetic field and the column density structure using this method, the simulation that has low magnetic field, the one that is dominated by turbulence, has a very different relative orientation to the one that is dominated by the magnetic field. In the simulation with weak magnetic field, what you see is that at all densities, the relative orientation between the magnetic field and the density is mostly parallel. You only see a stuff that is parallel to the magnetic field. As when you go to a simulation that is dominated by the magnetic field, you see changes in the relative orientation between the column density and the magnetic field from the low column densities where you have mostly alignment to the high column densities where you have mostly perpendicular. So an easier way of looking at that is with this parameter. So remember, positive, mostly parallel. Negative, mostly perpendicular. What we see is that the weak field simulation, the quasi-hydrodynamic simulation, never crosses this line. It's always mostly parallel. And the line that corresponds to the simulation that is in equipartition between the field and turbulence and the one of a strong field, it has this transition from mostly parallel to mostly perpendicular. Okay? So far, so good. This is important because then we're going to apply it to the data. So of course, we projected. We used some toy models that Stefan hates for simulating those grain alignment efficiency. That doesn't matter. Let's look at the data. So when you look at the data, you have to be careful on which molecular clouds you pick, because not all of the molecular clouds are in an environment that allows you to disentangle the signal that you get from the magnetic field from the signal that you get from the background. So around here, there's a very nice molecular cloud that is at 200 parsec, the Coalsack. That's great. It would be a great one, but it's on top of all how many spiral arms. We don't know how many feedback events, so we don't really know what is the magnetic field that is associated to that cloud. That's why we only select clouds that are off the galactic plane and that are reasonably close to us. So that leaves us with 10 objects, okay? So you'll notice that there's no California cloud, there's no pipe, although if you do this analysis on the pipe, it works, but we don't know why. Because the pipe is sitting in front of pretty much the galactic center, so there's no reason why all of the magnetic field behind the pipe is conspiring to produce this emission. So since we didn't understand it, we didn't put it, okay? So you see all of this are off the galactic plane. And then we did that exercise. So you have the map. This is the polarization, column density, and then we calculate the relative orientation using that gradient. And then you get a mess. But it's a mess that looks pretty much like what your eyes see. So if you look at this filament, that is the one that Doris studied, yeah, it's 90 degrees. So this is mostly perpendicular. Let's check. Yeah, it's mostly perpendicular. How about this fellow up here that is mostly parallel? It should be blue. Yeah, it's mostly blue. So yeah, we believe the method. But how do we summarize all of this information there? If you find this is a mess, you have to ask yourself how you were doing this before, because people do this by eye. So when you evaluate this map, you're ultimately trying to do by eye this thing. So it's very difficult to really quantify what is the relative orientation in a systematic way. So what we did is we split all of these observations in bins of column density. And what we found is that the bins of column density have a relative orientation that is mostly parallel. So the histogram peaks around 0, and the bins at the highest column density peak around 90 or minus 90. Of course, this is relative orientation, so it doesn't really matter if it's negative or positive. So you have a change from mostly parallel to mostly perpendicular in torus, for example. And if you summarize that using this parameter that, remember, I get from the counts on the sides and in the center of the histogram, it goes from mostly parallel to mostly perpendicular. Adults that actually know about the statistics have been helping us to devise a better way of quantifying that. So we use this thing called the projected radius statistic, and if you're interested, you can ask me later. But basically, we see the same trend using this much better tool that basically calculates deviations from a Foyn-Neumann distribution of angles, which is actually a Gaussian when you have a circular distribution of the variable. Okay, so we did that for the 10 clouds, and what we found is that most of the clouds present the same behavior. Mostly parallel to mostly perpendicular. There's some very good examples. So Chameleon, Mosca, Aquila, Orion more or less. All of them have this trend of going from mostly parallel to mostly perpendicular or undecided relative orientation. Okay? So we have that trend. So that is compatible with these clouds. So if you have this new tool, you can actually see the change is much more abrupt. So you see the trend is really changing for most of the clouds, from mostly parallel to mostly perpendicular. So this is compatible with the simulation that is either in equipartition between turbulence and the magnetic field, or where the magnetic field is dominating. But this is just a simulation, and these were just a few clouds. So there's not more Plancks. There's not going to be a Planck, at least for the next 30 years. So the only way that you have to do this on the same scales and in multiple colors is either Sophia, but Sophia is complicated, so you just go and build yourself a balloon. So we built BLASTPOL. So BLASTPOL is actually the box, one of the boxes of detectors of Herschel's Spire. And we just put a polarimeter and a halfway plate and all of that, and we flew it from Antarctica twice in 2010 and 2012. So this is me in 2012 doing one of the most important tasks in Antarctica, that is checking that that nothing changes in the experiment. So this is at 1 kilometer from the base where you don't have radio frequency interference. And we used to do this until one day I was there and there was a gust of wind and the whole thing tipped over. So it was me like dragging the whole thing, and after that NASA doesn't allow, and now we have like big straps there. So this is like a few minutes before I had to save the whole experiment. So that was painful. But in the end, we got really nice maps. And BLASTPOL has higher angular resolution and also has 3 colors. So we did the same experiment for a cloud that is a little bit further away. It's at 700 parsecs. And if you have higher angular resolution, what you can do is divide the cloud in portions and check how the different portions of the clouds are behaving. So historically, the Vela C cloud has been divided into these 4 portions, 2 that look like ridges and 2 that look like nest. And by nest, it's just a whole mess of filaments. And by ridge, I just mean one dominant filamentary feature. So when you do the analysis of relative orientations there, what you find is that the parts of the cloud that are like ridges, they have the clear trend of changing from mostly parallel to mostly perpendicular. Of course, BLAST is limited in reconstructing the large scales, and we don't have a very large map, so it's hard for BLASTPOL to reconstruct lots of points in that side, but we get mostly the part where you go from no particular relative orientation to mostly perpendicular. And it's the 2 ridges that are mostly and clearly perpendicular, where the 2 nests, they still have the same trend, but they don't have a clear change of relative orientation. Okay? So we have a morphological difference in behavior of relative orientation, but also the column density PDF. And just for the record, I hate this way they represent column density PDFs, but this is what is in the literature using the logarithm. But what we find is that the nests actually have a shallower column density, a deeper column density PDF, yet they have less maximum column density. And the ridges have a shallower column density PDFs. So this is very tight, no? Well, we still find that the ridges are behaving a bit different and the nests are behaving a bit different, but we have to convince ourselves that this is actually the case. So we run an experiment in a cloud that we have observed before. So this is the Aquila region that was, of course, included in the 2016 study with Planck. And we asked the question, what is the difference in the relative orientation between the left and the right portion of the Aquila region? There's nothing fancy here. I just trace a line in the middle of them and check how does the column density PDF looks and how is the relative orientation changing. So the column density PDF is very clear. Aquila right has a much steeper column density PDF, and Aquila left has a much shallower column density PDF. And when you look at the relative orientation, it's clearly different. There is no change of relative orientation in Aquila right. The one that has a shallow column density, the one that has a shallow column density PDF, this is like a tongue twister, is the one that is changing very steeply relative orientation. The other one is not changing relative orientation that much. So what do we make out of this? How do we understand these results in a broader context without like running an infinite amount of simulations? Well, you can first pose a cartoon, and then I'm going to tell you what we are actually thinking. So you have this change from mostly parallel to mostly perpendicular. So if you think of the physics of a laminar flow, Alex, don't jump yet. So if you think of a laminar flow, what the magnetic field is doing is behaving like your hair if you have Play-Doh. So when I do this example in Europe, nobody knows what is Play-Doh, but here everybody knows what is Play-Doh. So if you put Play-Doh in your hair, and then you have motions along your hair that would represent the field lines, you would stretch the Play-Doh along the field lines, and the only accumulations that you can have are perpendicular to the magnetic field. We think that is what is happening, but this is the description of a laminar flow. We know that the interstellar medium is a highly turbulent flow, so if you want to do this and have a serious interpretation of this change in relative orientation, you have to do it with the MHD equation. So this is going to be a little bit distressing for you. So here's a puppy. And here are the MHD equations. Okay, so we took two of the MHD equations. This is the continuity equation, and this is the Faraday equation. So these are relating the velocity field with the magnetic field, and just this is conservation of matter. And then we construct an expression for the relative orientation between the magnetic field and the gradient of density, which is the same thing that we were measuring with our method. When you plug that in, the solution to that equation is telling you that actually the relative orientation changes in that angle are related, one, to the divergence of the velocity, to terms of the velocity. So it really depends on the mechanics of your flow, what relative orientation you have. And also it depends on some of the details of how the magnetic field works. But just to make a long story short, there's two favored solutions to that equation. One is mostly parallel, and the other one is mostly perpendicular. So it shouldn't come as a surprise that what we're seeing is mostly parallel or mostly perpendicular, because those are the equilibrium points, and what drives you from one equilibrium point of mostly parallel to the other one of mostly perpendicular are divergence of the velocity field. So this divergence of the velocity field you can interpret can be shocks, can be gravitational collapse. This is what is causing the change in relative orientation from one to the other. Okay? So this is the current version that we have, but now we have to break it, no? Now we have to go back to the data and see if this actually works. So we have some clouds that actually work really well like that. So if you do now something that is just the mean relative orientation per column density bin, so for a particular column density bin, you trace what is the relative orientation between the magnetic field and the column density, well, you see the transition very well here. So you see it goes from 0, mostly parallel, boom, to mostly perpendicular. So this matches into that. So Chameleon Mosca also matches into that. But if you go to another cloud, to Orion, it's not as simple as that. So it goes from 0 up to close to 90. That's where we were interpreting that as changing from mostly parallel to mostly perpendicular. But it's not clear that it really goes to mostly perpendicular. By the way, this is a very important example because there's some people that have been linking the star formation of the clouds to the relative orientation. And this is an example that if you ever hear somebody talking about that, you should ask them. This is Orion A. It's forming 10 times more stars per unit of mass than Orion B, that is up here. And the relative orientation is exactly the same. So how can that be possible? That you have the same relative orientation trend, but their star formation efficiencies are very different. Okay, so is that because the magnetic field doesn't intervene? Is that the way you perform the star formation? So whenever you hear somebody claiming that, at least ask them the question, why is Orion A and Orion B so different in terms of star formation, but the relative orientation are basically the same? So remember that I was telling you about this change from 0 to not so much 90. What we found, if you closely inspect Orion, is that in Orion, when you look at the polarization signal, you're not only seeing the molecular cloud, you're also seeing an event of feedback. Actually, there's a star here, Kappa Orionis, that is making a bubble, and we're seeing that bubble in the magnetic field. So the bubble is actually blowing the magnetic field, and that changes the relative orientation. Remember that I was telling you whenever you have a divergence of the velocity field, you're going to have change in relative orientation. And here you have a mess because you have the magnetic field of the bubble on top of the magnetic field of Orion. So you have to be careful when you make conclusions out of a situation like this, where you have a complicated environment. But this is also promising because it allows you to study feedback using the morphology of the magnetic field. So that's something that we did before. So there's this paper on the Rosette Nebula that is just right behind Orion, where we study that the changing morphology of the magnetic field around the H2 region in the Rosette Nebula. Of course, the Rosette Nebula is really far, so it was hard to determine that change. But we're working in other regions, and we're working in other sources of feedback. So outside, there's a poster on this work that we just finished on the Orion Eridanus bubble. So the Orion Eridanus bubble is well known because it's one of the largest bubbles in the sky. Okay, it is thought to have been produced by multiple supernova explosions, and this thing is huge. It's like this big. When you go outside, this thing is like this big. Okay, so this will be the dominant feature in the sky, besides the galactic plane, if you could see just H1. So in this color diagram, teal is H1 emission. That's actually how they initially identified the bubble. Red is H alpha. So you're seeing here a transition from the neutral medium to some slightly ionized medium. And what we find is that the magnetic field is tracing very well the edge of the bubble. Okay? So what we're seeing is not just the magnetic field anchoring a particular molecular cloud. What we're seeing is multiple components, and in a neighborhood that is as complicated as Orion, this is not straightforward to model. Here, the circles and the triangles, they correspond to all of the Seaman observations made with H1 of the line of sight magnetic field. So circles means magnetic field pointing towards you, and triangles, magnetic field pointing towards the board. So we don't really know what the magnetic field is doing down here, although we know that it's associated with some of these features. So in the last few minutes, I'll just talk about my conclusions. If this is a framing talk, Planck is a framing experiment. It gives us like the large-scale picture of the magnetic field from which we can start drawing conclusions about smaller scales. And more in a local basis, so I found the change in relative orientations for the 10 nearby clouds. Then we went and checked that with the blast ball. And then we think that those changes in relative orientation are associated with larger scale processes of divergence of the field, either collapse or compression. But not only that, there's another lesson that we learned out of the Planck data, and is that we can use different techniques to explore the data in a more systematic way. So that is what I'm doing now in Heidelberg, where I'm working with the Thor survey. So I'm particularly working with the H1 part of Thor, and I'm comparing the H1 emission towards the galactic plane with the emission of CO, using a technique that is pretty much based in what I did with Planck, that is assuming that you can describe very well the morphology of an image using the gradient. So systematically, what I'm doing is just comparing the two velocity cubes and try to establish a correlation between them both. In simple English is how much one velocity channel looks like another velocity channel in another cube. That is what I'm doing. So when you do that, you actually recover. This is just for a small example in a small velocity range. So this is velocity of CO, and this is velocity of H1. For a small portion of the Thor data, we found a very nice correlation between the H1 and the CO, as you would expect it. But this is actually morphologically seeing it. We're seeing CO nested inside of the H1, just from morphological arguments. And with that, now I'm really going to my conclusions. So don't forget to visit plankandthemagnetic.info. And I really have to run after in the afternoon, like at 3 or 4. So I'll be happy to discuss any of this before I go. Thanks very much.
What is the thickness of your channels?
That's a good question, Alex. So in this case, these are very broad channels. So you're right. You're dominated in this case by the large scale motion of the bubble. So we intentionally use very broad channels to do the study of the Orion Eridanus bubble. But in this case, when we study Thor, it's actually one of the parameters that you can tune around. So you can use single velocity channels and check the perturbations that are caused mostly by the velocity field. But you can also broaden your channels and look for some more large scale features. So the answer is both.
And what did you see a significant difference?
Yeah. So with the small velocity channels, it's harder to identify by eye actually where is the correlation coming from, because it's probably some velocity fluctuations. So it's much harder to identify when the velocity channels are very narrow. If you broaden them a little bit, then most likely you're sampling some larger scale. So it's just from the point of view of morphology, if you make the velocity channels broader, then you can see it right away, like in Orion Eridanus.
I think in one of the conferences, you showed just that same plot, and you showed that not the correlation over. Yeah. That one of the diagonals was the correlation between the CO and H1 because of the cloud. Have you found something similar but for bubbles? H1 bubbles and maybe 30 CO bridges of bubbles?
Yeah, so actually that's how I got this job. So we found a bubble that actually is very well traced by both. But see, this is a new technique. So it's very simple. I'm just calculating gradients. But it has taken me 3 years to convince people to start doing this systematically with the polarization. So learning my lesson, I want to do something very simple. So this is made in a region where we know we have a HISA feature. So first we have to be in solid ground of seeing something that people are more familiar with and something that is easier to simulate, and then we're going for the bubbles. But yeah, the answer is yes.
Another bubble-related question.
only Orion or
Yeah,
Orion?
no.
Okay.
So Barnard's loop there, I don't see Barnard's loop very well in the pattern that you're showing, and so that's mostly a feature in the ionized gas, and so it just makes me wonder whether you can say anything. I mean, if you look for bubbles all over the sky now with this, right, and those are obviously traced by dust, if you're seeing the dust polarization. Can you say anything about like the coupling of the field to the ionized gas if you also look at the synchrotron data? Or?
So we have to increase the statistical sample. So we can do it blindly and check which ones do match, and then try to explain why the ones that don't match. For example, when we started with Planck, like step 0 Planck, we thought that the lambda Orionis bubble was going to show like a very nice feature in dust. We didn't see anything. But there's some other bubbles in H alpha that are very well traced by the magnetic field. So it's a matter of checking how bad is your background. So we know that there's a lot of material behind lambda Orionis. So most likely we're dominated by the background. Or maybe this bubble is so old that the magnetic field has already diffused.
I can show you later an ancient optical background polarization map that shows Barnard's loop very clearly in the dust absorption mode.
So that would be a clear imprint that the stars that you're seeing are probably closer, so they're tracing the Barnard's loop. But with 80-inch left light, we look into the line of sight depth with dust, and this is a very deep line of sight. Actually, it's the same reason why you don't see the California molecular cloud. So in this paper, we focus mainly in south of -20, simply because it's the part that hasn't been traced by any starlight polarization. In this area, below this line, there's, I think, 16 starlight polarization observations ever made.
In distinguishing weak field and strong field in a lot of your analysis, what's sort of the dividing line between weak and strong?
That's a good question, Phil. So that goes to the simulations that we initially used to characterize this. So the simulations that we initially used were an isothermal box, and we call it strong and weak with respect to the thermal pressure. But then it's a combination of having decaying turbulence. So basically, the difference is in beta, in the beta parameter. So beta of around 0.1 for a strong field, and beta of 100 for weak field. So that corresponds to 3.6 microgauss for the strong field, and for the weak field, it's like 10 to the -3 or something like that. It's very small.
So, okay, there are no questions left. Thank you again.
Thank you.
Just as a reminder, we have now the picture take
Oh, yeah,
session.
is that right? We're done with this session? Okay, great. So there's going to be a picture outside. We'll put some stairs right outside, and they make for a very good picture. Anna, you have the camera. Anna has the camera, and Sarah.
Héctor, sé que esto va a mostrar ahora la burbuja, pero pues en principio esto lo puedes usar para cualquier objeto. O sea, si tienes algo en mente.
No, yo quería hablar contigo, pero me tengo que ir ahora, pero tú estás en Alemania, ¿verdad?
Sí, estoy en el Max Planck.
Porque escribo, me tengo que ir ahora en la foto, pero podemos hablar un poquito ahora. Sí, me gustaría pasar, bueno, yo estoy interesado en burbujas también. Tengo una estudiante, pero subgraduada, sí, buscando bobos. Empezó con Galfa, pero cuando vi que había salido los datos de Thor, pues la puse a ver si los veía en Thor, en los datos de Thor también.
Okay.
Pero era para ver si se veía algo relacionado con los bobos que se habían identificado en Glimpse.
Pero tenemos un paper en eso, el paper de Lorraine Anderson.
Bueno, lo que pasa es que no es lo mismo.
Sí,
no son supernova remnants.
Son supernova remnants.
Ella está buscando alrededor de H2 regions.
Sí.
Y es una subgraduada que más bien para que tenga experiencia en investigación.
El código en esto es completamente disponible. Se llama AstroHog. Y entonces, sí. Entonces, te puedo enviar el GitHub. Si me envías un correo recordándome, te puedo enviar. Y ahora estoy buscando gente que comience a usarlo.
Sí, no, eso sería interesante. Quiero pensar más en qué buscar en correlación y eso. Porque con la cantidad de datos que hay ahora, ya no sé. Antes yo lo hacía a ojo, pero ya no se puede hacer a ojo.
Sí, ya toca sistemáticamente. No, avísame.
Ok, perfecto.
Claro.
Okay. Bueno.
Super.
Sorry, hi, that was fantastic.
Yeah, that was good.
Thanks, Elisa.
I didn't realize you had done the Rosetta too. Did you actually measure a B field?
Yes.
So did you compare it to feedback theory that I did?
No.
So you don't?
Because we didn't know about you at that time.
So why don't we start there?
Yeah.
That's literally that's a 30-second calculation of pulling up the numbers representing.
Well, let's get the numbers. It's happening after the picture. I can just like
Like,
pull it out.
literally, like we just put the numbers in and we can check whether it makes sense.
Yeah, let's do it. Hey, why didn't you think of that?
Oh, yeah, yeah. Here, wait, you have to put yours back here, right?
I think the numbers will actually. No, but it's ballpark, right? I mean, he told me it was one. He told me it was 500, and the thing had already accelerated to 10 parsecs or 50 parsecs. Then that was what I did. So
Actually, no, yeah, go ahead. You come be the picture, Claire. Go ahead and write. So I can't come in the afternoon, and I have to go to that.
Okay.
So either way, I can't come. But John's thing is here, and the long film is here. So you might want to do it afternoon.
Oh, okay.
So I don't know. It's up to you. But I'm telling you, because like Catherine's here.
Oh, wait, so what? Wait, Catherine,
Next time Kate comes, well, let's hope that's which one? I don't. We'll see if people even want it. Okay. So wait. Hello? Just in case I confused anyone. Sorry, hello. Hi, everybody. Just in case anyone is confused by what I said before, these are the charts for the unconferences. If people want to write stuff down now, that's great. And then we're going to go across the street now for the coffee break in Pforzheimer House, as it says on the schedule. Didn't mean to be confusing. We'll bring these pieces of paper with us. Thanks.
You signed me up, thank you.
I did.
For doing that.
I did. Hi. Did you get like a huge score in bowling last night?
No, absolutely not.
Somebody got like 100. Is there someone else in the end?
Yeah, that's
You can vote or you can propose one.
Yeah, I'm gonna. So, but what are those?
These are the 3 rooms or 4 rooms, and then this is the name of the session. Your name.
This is the session. Okay, there's it.
Lisa, do you want me to take those over?
Awesome.
Okay.
Great, thanks. And just grab a marker.
Okay,
There's
yeah,
probably
sure.
more on the other side.
Yeah.
Thanks. There's some on the bench there.
You wanted to have a meeting today.
we taking these? Okay.
Yeah.
No, it's okay.
Okay.
No worries. Yeah.
I usually